Okay, so I think I'll just focus on the differences because more or less the basic idea will be the same. So let me just skip all this. So one thing is why are we doing the models? So that is a very important. Why do I need to do this? There is a lot of effort. So why do I need to do these models? So the idea is that if you think of this room as, let's say, the city of Vellore, and let's say there's a monitor in one of the benches, and I want to use that air pollution exposure or temperature exposure for everyone sitting in this room, then the people who are sitting close to that monitor, they would have a better estimate of exposure than, let's say, if the monitor was this side, you are underrepresented in terms of, so your exposure will be miscalculated. And now let's say there are 5 different monitors, even then there would be a large gap in between where you have people living but you don't have their exposure. So the idea is to fill those gaps. So you need to have everyone's exposure. So if I create a grid across this room, I use the model or the monitor and the predictors that are there, build a relationship between, let's say, PM 2.5 and the predictors. Once I have that relationship, then I can predict wherever you want. Like if you have the predictor variables in those grids, you can always get an estimate of whichever outcome, whether it's PM 2.5 or temperature. So the idea is to fill up gaps. So the monitoring in India is mostly focused, especially for PM 2.5, it's mostly for urban centers, right? So you don't have monitors in, let's say, most rural areas, which has a lot of population. A lot of peri-urban areas or tier 2 cities, tier 3 cities, they don't have monitors, but they have a lot of people living there. So how do we get across that barrier? And it's difficult to maintain monitors, and like each monitor, I mean the Central Pollution Control Board monitors, they are very, very costly, and the cost of maintaining them over the years, that's an added cost. So you can't just go ahead and put 5 monitors in a small city. That's not going to happen. So we need to come and innovate in terms of how do we want to assess exposure. So that's why we are doing this. So this was part of a project which we had started in 2016. So this was the GeoHealth Hub, and the idea was to start in 2 cities, Delhi and Chennai. And because we had a cohort there, so there were people who were being monitored for cardiovascular and cardiometabolic diseases, and then we wanted to link up the exposure to PM 2.5 with these outcomes. So that was the motivation. So spatially so there are 2 things, one is spatial and one is temporal. So you need a spatial predictor, you need a temporal predictor, and some variables or some predictors are both spatial and temporal. So a basic idea is that what is the most important part of the model is the ground monitoring data, which is your gold standard. You will calibrate your model based on that. So remember when I said there are monitors in 5 different locations. You only have the outcome data at those 5 different locations. Outcome meaning PM 2.5 or temperature. The rest of the places you don't have the thing that you are wanting to model. So you want to model the relationship of PM 2.5 with predictors. The actual value of PM 2.5 is only there at the monitoring stations, not everywhere. But that is the most important part of the model, the data that you will calibrate against. And then you have a bunch of predictors. So you have satellite data, meteorology, land use, and that you have a lot of it. So most of it is publicly available and at different spatial resolutions, different temporal resolutions. The main bottleneck is the monitoring station data. So this is the same heat map but for PM 2.5. So the darker colors you have more data. So again the numbers are percentages. So this is around 15% of the data. So 15% of the data comes from the north zone in the last 3 years. So this was done from 2008 till 2020. So you will see if 15% of the total data is coming from one zone in the last 3 years, there is a lot of inequality in how air quality is measured. Most of the focus is in the north zone because of Delhi and a lot of monitors in and around Delhi. So that's why the unequal distribution. So this needs to be taken care of when you are building your model, so that you don't over-represent the north zone. So this is more or less the same approach, but maybe I'll. So did you get how we are doing the split? Any doubt about that? So how are we splitting monitors? Because we are leaving out monitors, not observations. So if we had, let's say, 1,000 monitors, we are leaving out 200 monitors for validation. How do we select that 800? The 800 monitors on which your training will be done. How do we select it? So there are 2 or 3 aspects. One is data availability. Each monitor is contributing some percentage of the data, right? So if I think of this 100%, this is coming from different monitors. So let's say one monitor which came up in 2016 and has been running for 4 years versus a monitor which is running from 2008 and is still running, that contributes a lot more. So each monitor would have some data availability, or how much contribution is it making. So if you have this data availability as a variable, you can create strata out of that. So you can have monitors that have very little data. This will be the first, let's say the lower 10%, then 10 to 20%, 20 to 30%. So monitors which are contributing a lot of data, they would be in the top strata. So this strata is giving you what? So this is giving you monitors by their data availability or how much contribution. So you want to make sure that you are sampling equally across strata so that you don't over-represent. So if you have done it randomly, you might end up with a lot of monitors which have a lot of data, because we are splitting by monitors. So we are selecting 800 monitors. If you do it randomly, you might end up in your training data set, you might end up with all the monitors that were from the north zone. This might happen. What would the result would be? You would have an over-representation of the north zone, or the relationship. So the idea is to obtain a relationship between PM 2.5 and predictors which work across the country, which is validated across the country. So if you are only training on monitors in Delhi, that's not going to be a good model for other parts. So that's the one strata that you have to do. The other one is the zone. So if you leave it random, even after you do the data availability part, there are monitors which are long running in urban, like metro cities. So if you don't split by zone, you might end up with most of these things in, let's say, few urban centers. So you want representation across zone and you want representation across data availability. So that's the strategy that we had to follow for India for PM 2.5, so that you have representation both in terms of data availability as well as zone. There can be additional, like you can have other strategies as well included in this. So things like spatial mapping. So if you are trying to make sure that if the 2 monitors, so no 2 monitors in your training set should be in a distance of less than 5 kilometers. So what would happen if you don't do that is, let's say you end up selecting monitors which are basically very, very closely related. So if there are 2 close monitors in very close proximity, they are basically giving you the same information and you are double counting. So that's another layer of complexity. For this model, it was enough because there were fewer monitors and they were spread out across. So since we were doing it by data availability as well as zone, that problem doesn't arise that much. So if you have a lot of data in specific centers, then that becomes a problem. So the method is more or less similar. So there are some things which you have to do beforehand. So since we have, let's say, 100 or 150 different predictors, there cannot be any missingness in that data. So every predictor needs to have all the values for whatever period of, because remember that we are doing this for every day. So the idea is to get PM 2.5 averages for every day from 2008 1st January till 2020 31st December for every square kilometer of the country. Your calibration data or the monitor data is only at monitors, so 1000 locations or 800 locations for the training set. But every data, like the predictors need to be complete. You cannot have missing values. If you have missing values, it will not give you a prediction. So that needs to be cleared out first. So most of the reanalysis data sets you don't have missing because they are reanalysis, so they are model data. So that's already there. There are things like satellite data which have, so AOD is one very good example. So there's a lot of missingness in AOD data, which is aerosol optical depth, because of cloud cover or other issues. And you have to fill them up. So how do you fill them up is a different imputation. So there's a separate machine learning model which fills up AOD. That's a separate step before you can come to the machine learning part. Before you come to the PM2.5 model part. Once everything is filled up, now you have a data set which has PM2.5 observations and predictor values at monitoring stations. The monitoring stations are basically in a grid. So if you have 3.5 billion grids in India, those 1000 monitors, they are falling in 1000 of these grids. So the whole country has, let's say, 3.5 million or billion grids. Out of them, only 1000 grid cells have data, because that's where the monitoring stations are. So that is your whole, this full data set is basically that, observed PM2.5 and predictors. The rest of it, you have the predictors, but you don't have PM2.5, and that is why we are doing the model, to predict PM2.5 at places where you don't have PM2.5 observations. So once you have this data set, then you split. So splitting is again by leaving out monitors. So you leave out 200 monitors using that same strategy, and the remaining 800 you train your models. So this one uses 4 different models. Once you have got these models, you don't, so now you have to go back to the data that was not used for training, and you predict in that validation data set, which is the monitors which were not used for training, you predict. So remember that that data set also has observed PM2.5, because those were the remaining 200 monitors. Once you have the predictions from each model, you can compare with the observed PM2.5 for those left out monitors, and that is what gives you prediction accuracy. So in a prediction model, this is the difference between estimation and prediction, because prediction, you have to leave things out and test your model performance there. So if you have done a regression analysis, it will always give you an R square, right? It gives you an R square. What is that R square? That is a meaningless thing, because what your objective in a regression is to find out that effect estimate. The R square is a model fit. The R square shouldn't be calculated in the whole data set. If you left out a part of the data set, build your model and then test on the remaining data set, that R square is much more valuable to figure out whether a model is good or not, a predictive model. So that's why we are leaving out the monitors, getting the predictions, comparing the observed and the predicted in the left out monitors. So then once that is done, we combine the 4 different predictions using a Gaussian process. So it's like an ensemble. So you average across the different predictions and get a final prediction, one prediction for each grid cell. And there's an additional step of regression calibration, which is for correcting that measurement error. So let's say you are systematically overestimating or underestimating in specific regions. You can get that estimate from this validation data set. Once you have that estimate, you can correct. So that is the correction for measurement error. This is not necessary, but for epi studies, it is recommended that you have a measurement error correction, because once you are using these PM2.5 predictions in your epidemiological work, if you don't do the regression calibration, you are assuming that it is a correct estimate. So it is not corrected for measurement error. So that additional step is only for measurement error corrections. So these are the maps. You can look at the publication for more detailed ones. But you will see that, so this is the annual average. So you have daily averages. So daily average PM2.5, once you have that, you can do these 1 week or 1 day studies. If you just had annual averages, you wouldn't be able to do this study anyway. So why you would need this is, one, because of spatial gap filling, because you can do this study in, let's say, a hospital where you don't have PM 2.5 data in, let's say, in the nearby 20 kilometers, you can still do it. The other thing is the temporal accuracy or the temporal precision is because you have daily averages. So now you can create your, whether you want to study short term, like extremely short term, like yesterday's averages or last week's averages. That's the powerful, like what is the use of the data set is because of that. So you can do both short term and long term studies, and you can do it across the country, wherever you have health data. So I think we'll stop here, because the next steps would be doing the actual health effects analysis. So any questions for this? Sorry, yeah?
Can we reuse this PM 2.5 for our any epidemiologic analysis?
It is publicly available. So right now it is available from 2008 till 2020, and a lot of people have already used it. It's on Harvard Dataverse. I think we can provide a link.
We'll put the link up for anyone who wants to download and play around with this data set. If you are wanting to use it, please go ahead. Feel free to use. Just cite us if you're publishing. And if you need to have any more things clarified, you can always reach out to us.
Yes, so there are district level averages as well, which are much easier to deal with. But there are, if you want daily averages, those are there. So every day, every square kilometer. But you need to process that data. It's in raster. I mean, you download it and use it, because downloading the whole country's data that's simple, but you need to figure out which, because you might not be doing a study for the country. You might be doing it in one specific, let's say a district, or a few villages, or a few cities. So you need to figure out which space you want to focus on, extract the data from the rasters, and then make your own averages. So whether it's a one day or, I mean, the averaging is up to you. So that depends on the outcome also. But it is publicly available. Both, I think, PM and temperature, both are available. And so we are updating them. I mean, we'll get more predictions for 21 onwards. So that will be there. I mean, maybe in few months it will be there.